Hi again, this is Rodolfo Eric Angat, your teacher in Earth and Environmental Science. Today we'll be learning about Kepler's laws of planetary motion. Our essential question for today is, how do I explain Kepler's three laws of planetary motion? This lesson covers Standard 1.1.1. With this lesson, we aim to achieve the following competencies. The first one, I can identify Kepler's three laws of planetary motion. The second one, I can draw the figures and equation that represent Kepler's three laws of planetary motion. Third, I can define elliptical orbit. Fourth, I can measure the distances in the solar system using the astronomical unit. And lastly, I can determine when an orbital speed is faster or slower. Let's begin with the astronomical unit. What do we mean by the astronomical unit? Astronomical unit, or AU, is the average distance between the Earth and the Sun. The value of one astronomical unit is 150 million kilometers or 93 million miles. This is the average distance between the Earth and the Sun. We use the astronomical unit to measure distances in the solar system. Like in this table, you will see the distances of the various planets in comparison to the distance of Earth from the Sun. Earth's distance is one astronomical unit, which is equivalent to 150 million kilometers or 93 million miles. If you will look at Jupiter, its distance is 5.2 astronomical unit, which means that Jupiter is more than 5 times farther from the Sun compared to Earth. And Uranus is more than 19 times farther from the Sun compared to Earth. So that is how we use the astronomical unit. Again, it is used to measure distances in our solar system. All planets orbit or revolve around the barycenter of the solar system in a counterclockwise direction. So this is counterclockwise. And this has been happening since the formation of the solar system. Our solar system is located in the galaxy known as Milky Way Galaxy. The Milky Way Galaxy is an example of a spiral galaxy, and it is just one of the so many galaxies in the universe. Our solar system is located in one of the arms of the Milky Way Galaxy, and it is just one of the many solar systems found in the galaxy. The diameter of the Milky Way Galaxy is 100,000 light years. And remember, this is just one of the so many galaxies in the known universe. Another galaxy that we know of is the Andromeda Galaxy, also known as M31. The Andromeda Galaxy and the Milky Way Galaxy are in collision course with each other. Their current distance is 2.54 million light years away. So that's a big distance. To understand about light years, we have to remember that the distance between the two galaxies is 2.54 million light years, and they are in the collision course with each other. The speed of light in a vacuum, that is in space is a vacuum. The speed of light in a vacuum is 186,282 miles per second, or about 670 million 616,629 miles per hour. That's the speed of light. And if you have 2.54 million light years, that means you are traveling in the speed of light. If you are traveling in the speed of light, you will still travel 2.54 million years to get there. As of now, there is no known ship that can travel at the speed of light. But we did break the sound barrier though, but we haven't found a way to create a ship that can travel at the speed of light at this moment. So let's go to our main topic today, Kepler's laws of planetary motion. Kepler's three laws describe how planetary bodies orbit around the very center of the solar system. So, again, there are three laws under the Kepler's laws of planetary motion, and each law describes a specific idea. Let's begin with the first law. Planets move in an elliptical orbits with the sun as a focus. Remember the key word for the first law, elliptical orbit. The second law, a planet covers the same area of space in the same amount of time, no matter where it is in its orbit. What you have to remember on the second law is that it covers the same area of space in the same amount of time. And the third law, a planet's orbital period is proportional to the size of its orbit. These are Kepler's three laws of planetary motion. To learn more about them, let's use pictures. The first law states that orbits are ellipse or elliptical. So this is the orbit right here. It is shaped like an ellipse. The second law talks about equal areas in equal times. So you will notice the shaded parts here. These shaded parts do not have the same shapes, but they do have the same area. That is the second law, and we'll learn more about it as we proceed. And the third law refers to the orbital velocity and distance from the sun, also known as the law of harmonies. Now, let's focus on the Kepler's first law. Orbits are elliptical. The orbit of a planet around the star or about a star is an ellipse with the star at one focus. So this is the star. In this case, this is the sun and this is the earth. So this is exaggerated, but I just would like to show you that the orbit of Earth around the very center of the solar system is not circular. It is more flattened. At certain point in time, Earth is closest to the sun and that is called the perihelion. And when Earth is farthest away from the sun, we call that the aphelion. Now let's go to the second law. The second law states that equal areas in equal time. So let's look at this figure here. In 10 days, Earth traveled only this much orbit. See how slow it is covering its orbit when it is farthest away from the sun compared to when it is closer to the sun. In the same amount of time, which is 10 days, it covered this much orbit. In Kepler's second law, you do not only measure the orbit that was covered, you also measure the distance that was covered. In this one, though the orbit that was covered in 10 days was short, you'll see that it's elongated, like it's cover more areas from Earth to the sun. So this blue shaded part here is of equal area with the blue shaded part here. This figure here also shows us that the planet, our planet Earth, revolves slower. That's why it only covered this much orbit when it is farther away from the sun, and revolves faster when it is closer to the sun. That's Kepler's second law. Now let's compare it with the first law. With the first law, when you see this figure, you don't see the shaded parts. You only see the orbit, which is elliptical. Thus, this represents Kepler's first law. In Kepler's second law, you see the orbit, which is elliptical, and you also see the shaded part, which shows us Kepler's second law. Now, this is another figure representing Kepler's second law. There are three shaded parts. All three shaded parts have equal areas, and they all consume the same amount of time. When it is closer to the sun, it can cover longer orbit. Midway, it can cover a little bit longer or a little bit shorter, I'm sorry. And then when it's farthest, it covers the shortest orbit. But the areas are all equal. This is also Kepler's second law. Whenever you see the shaded part, remember that each shaded part is of equal area. You will also notice in this animation that when Earth is closest to the sun, it revolves faster. When it reaches this point here, it moves slower. This phenomenon is the reason why the length of time of the seasons are not all the same. Remember, when Earth is farthest from the sun, we call it aphelion. And when Earth is closest to the sun, we call it perihelion. Kepler's second law compares the orbital velocities of planets. Mercury is closest to the sun, so it is the fastest. As you move farther away from the sun, the velocity becomes slower and slower until you get to the last planet, Neptune, which is only 3 miles per second. Not all seasons are created equal. Winter is only about 89 days. Fall or autumn is only about 90 days. Spring is only about 93 days, and summer about 94 days. Winter is the shortest, while summer is the longest. So, why are there 93 days in summer and only 90 days or 89 days in winter? I have to correct that. Now, going back to this one, you have to remember that when Earth is closest to the sun, it is winter in the United States. And when it is winter, Earth orbits faster. When Earth is farthest away from the sun, it is summer in the United States, and Earth orbits slower. And that's the reason why summer is longer and winter is shorter. Please do remember that the reason why we have seasons is not the Earth's revolution around the barycenter of the solar system, but rather the Earth's tilt. To say it clearly, Earth's tilt results to the uneven heating of Earth's surface, which gives us the seasons. Okay, let's go back. As the Earth revolves around the barycenter of the solar system, our view of the night sky changes. The constellations The stars, the asterism that we see in the night sky are not always the same. Of course, except for the northern star Polaris. Orion is most visible in the evening sky from January to March, that is winter, while Leo is most visible between March, April, and May, and that's spring. And Scorpius is visible in July to August, and that is summer. When the calendar was not yet invented, this is how the farmers knew when to start planting and when to start harvesting. The stars in the sky change positions depending upon the seasons. Okay? But remember, seasons are caused by Earth's tilt, not by Earth's revolution. Let's now go to the third law of Kepler's planetary motion. What is Kepler's third law? There is an equation for Kepler's third law, and it is p squared is equal to a cubed. P is the orbital period, while a is the astronomical unit. Kepler's third law is a mathematical formula. It is a combination of the first and the second law. It means that if you know the planet's orbital period, then you can determine the planet's distance from the sun in astronomical unit. Now let's try to solve this one. On the first column, we have the planets. Second column, we have the average distance from the sun in astronomical unit. And the third column, we have the orbital period. And the fourth column, we have the radius of the planet. Let's say we want to determine the average distance from the sun of the planet Jupiter. And since we know the orbital period, which is 11.9, by using this equation, we can find the value of this one, or the average distance of Jupiter from the sun. So find the average distance of Jupiter from the sun using the equation p squared equals to a cubed, where p is the orbital period, right there, and a is the average distance from the sun, right there. Let's begin. So the orbital period is 11.9 years. So that would be it, 11.9 years. So using the equation p squared is equal to a cubed, 11.9 years squared is equal to a cubed. That would be 11.9 times 11.9 would be 141.61 is equal to a cubed. So to get the value of a, we have to cube root the 141.61, and that would be 5.21 astronomical unit, which is close to that one. Okay, so that's how we use the equation for Kepler's third law. Again, I hope this review prepared you well to answer the questions that you'll be answering in the MC lesson. Just to further review, let's go back to the very first one. Kepler has three laws. First law, elliptical orbits. Second law covers the same area of space in the same amount of time. Third law, a planet's orbital period is proportional to the size of its orbit. The third law is a combination of the first and second law. And the figures that you have to remember about the three laws are here. Elliptical orbit, equal areas in equal time, and the law of harmonies. Again, thank you so much for participating. Thank you so much for learning, and good luck. Bye-bye.